All right, now this is essentially the same as example 5, except now we have a table with more values. It's the same vehicle, we just have sampled the velocity every 1 second instead of every 2 seconds like we had before. So the idea here is that if we sample the velocity more frequently, we'll get a better estimate of the distance that this car traveled using the left and right hand Riemann sums. All right, so I'm going to do some of this offline so that you don't have to watch me try to graph this thing, and it takes up a lot of time. So, but what I'm going to do is the same as I did before. I'm going to plot these points. I'm going to, and then I'm going to estimate the distance traveled using rectangles, right? I'm going to do a right-hand sum, and I'm going to do a left-hand sum and then a right-hand sum. All right, so I've plotted the points that are in the table, right? And in the green line represents just me connecting the dots, right, with a nice smooth curve. And then these red rectangles represent the left-hand sum. So I'm going to call it L10, right, because there are 10 subintervals, right? So n is equal to 10. N is the number of subintervals. And each interval has a width of 1 second, right? So the width of each one of these rectangles is 1 second, and the height of the rectangle is determined by the value of the velocity on the left-hand side of each interval, right? So these red rectangles represent the left-hand sum. So I've written it all out here, right? Oops, I think I made a mistake, didn't I? All right, I made a mistake, so that's good. A lot of people make this mistake. Now, if I have 10 subintervals, I just take the first 10 values. Notice that there's 11 values in this table, right? So I started out at 20 feet per second. But because I have 10 subintervals, I should only have 10 values. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. This 50, I don't need that. I don't need that one, right? I went too far, right? I just wanted, because that last rectangle has a height of 49, right? Because I used the value on the left-hand side. So I basically just took let me see if I can draw this. I just took the first 10 velocity values in the table. Okay, so now let's put it in. I'm going to put it in my calculator, and what do I get? I get 371 feet. Okay, so that's my left-hand sum. That's an estimate. That's my estimate using the left-hand sum. Now, again, it's an underestimate, right? The velocity is increasing, and so the left-hand side of each subinterval is lower than the right-hand side, so that's going to be an underestimate. All right, now let's do the same thing, and let's do the right-hand sum. All right, so I've drawn in these blue rectangles which represent the right-hand sum. All right, I'm going to call it R10 because there are 10 subintervals, and the interval width is 1, right? So each rectangle is 1 by some height, and we're using the velocity on the right-hand side of each subinterval as the height of the rectangle. Okay, so I'm going to skip the first velocity, right? Because that's only on the left-hand side of the whole interval from 0 to 10. And I'm only going to take the last 10 values, and those represent the right-hand velocities. So that's what I've done. I've written down all of the numbers I'm going to put in my calculator so that I get some extra credit if I accidentally type something wrong in my calculator, right? So when I add that up and multiply by 1, I get 401 feet. Okay. All right, so that's my right-hand Riemann sum. Okay. Now, again, I can average these two if I want to get a little bit better estimates, right? Because I know it's got to be somewhere in between, right? The left-hand sum is an underestimate because the function, the velocity is increasing. The right-hand sum is an overestimate. So if I find the average of these two. I'm just going to take 371 plus 401 over 2, and I get an average of 386 feet. Okay, because I'm just averaging to get something that's in the middle, right? That gives me the exact middle between 371 and 401. All right, so notice that the difference between the left and the right hand sum here is 30 feet, right? So there's a difference of 30 feet, and that's 15 feet from 386 in either direction. 386 is right in the middle. Whereas if you compare it to what we had before, right, let's go back to the last example, the difference between those, the left-hand right and right-hand sum was 60 feet, right? The difference between 360 and 420 is 60 feet. So by sampling the velocity, more frequently, basically twice as frequently, I got a much better answer. I got the range, the estimate is better, right? Because this is saying, okay, the distance I traveled is somewhere between 371 and 401, right? Plus and minus, plus basically 386 plus and minus 15 feet, right? Whereas with my estimates before, it was somewhere between 360 and 420 feet plus or minus 30 feet. Okay, so we get a much better answer if we sample the velocity more frequently. So like I said, these are called Riemann sums, and they're the basis of what we're going to be studying in this next chapter, basically chapter 5. I skipped ahead to chapter 6, so I could do some work with linear motion again to hopefully give you that conceptual understanding of what we're doing. But if we just sample the velocity more and more and more and more frequently, we'll get better and better and better answers, right? So here this is just looking at, okay, what if we did it, if we sampled the velocity every half a second, which would give us 20, n equals 20, right? Or maybe we do it every quarter second, right? So then n is equal to 40, right? And if we let n go to infinity, right, we're doing a limit, as n goes to infinity, what we get is the actual distance traveled by this with whatever this is, this car, right? This car. So, and that's where we're going with this. We're going to use these simple estimates, right? The simple estimates assuming constant velocity over each time interval, and to estimate to get better and better estimates of the actual distance or displacement that this vehicle traveled. All right, that was, I'll see you in the next video.